All right, in this lesson, section 11.3, we are leaving, well, sort of leaving permutations and moving on to another way where we arrange items, but in this arrangement, which these are called combinations. In combinations, order does not matter. Now, let me see if this makes sense. Suppose that you had 5 people and you were going to select 3 of them to be president, vice president, and secretary. And the first person you chose would be president and the second vice president and so on. Then how many ways could you get that slate of officers? That would be a permutation because it matters whether you're chosen first, second, or third. If instead you are going to choose 3 people from the group of 5 to be on a committee, just 3 members of a committee, it wouldn't matter if you were chosen first, second, or third because you would still just be a committee member. So that's the difference between permutations and combinations. And the formulas are different. Here is the combination formula. It's n factorial over n minus r factorial times r factorial. You're dividing by more. So the combinations will not be as many as the permutations were. On the TI-84, you'd start at a home screen, type in your N, math, probability, and then NCR, and then you'll type in your R value. So let's take a look, and we will see if we can tell the difference between when we should use combination and permutation. Let's look at number 1. Determine whether the following problem involves a permutation where order counts or a combination where it doesn't count. We're not going to solve it, we're just going to decide which one. A medical researcher needs 39 people to test the effectiveness of an experimental drug. If 97 people have volunteered for the test, in how many ways can 39 people be selected? You have to ask yourself the question, does order matter? Is being chosen first any different than being chosen 23rd? And the answer is no. And since order does not matter, this is a combination. All right. Number 2. How many different 3-letter passwords can be formed from these letters if no repetition of letters is allowed? All right, now, does order matter? Well, suppose we had the password QRS. Is that a different password than SRQ? Because they were the same 3. Yes, those are different passwords. That means that the order that they're selected to make the 3-letter words matters. So that is a permutation. If the order affects it, then it's a permutation. We'll do some application problems in a few minutes, but let's practice with our calculator doing the combinations. You certainly can also practice, if you want, using the formula. All right. I'm going to clear. And I'm doing 6 taken 5 at a time. I have 6 items and I want to know how many different ways I can grab 5 of them, and the order doesn't matter because it's a combination. So 6, math, over to probability. Now I'm choosing number 3. And I'm taking them 5 at a time, and there will only be 6 ways. If I wanted to write it out, it would be 6 factorial over 6 minus 5 factorial times 5 factorial. 6 minus 5 is 1. 1 factorial is 1, so that's irrelevant. This is 6 times 5 factorial over 5 factorial. Divide out, and that's another way I could have gotten the 6. I'm just going to use the calculator though. All right, number 4. I have 7, math, choose number 3, and I'm taking these items 4 at a time, and it is 35. And I do want to show you something. If I had done the same problem, 7, but I had done a permutation, which I was not supposed to do, but I just want to show you the difference. Look how much larger the permutation is, because when order matters, then there are more choices. All right, number 5. 6 taken 3 at a time. 6, math. Number 3, I'm doing my combinations. I'm taking them 3 at a time, and I get 20. Number 6, I have 11, math. Combination is number 3, and I'm taking them 1 at a time. That gives me 11. And this is probably getting a little bit boring. I'm gonna skip a few of, well, yeah, I'm gonna skip a few of these. Don't forget, you can work with 0, and there was something earlier that said, in fact, let's just do that one. We have, the formula says that is 16 factorial over 16 minus 0 factorial times 0 factorial. 0 factorial is 1. 16 minus 0 is 16. So this is 16 factorial over 16 factorial, because remember that was equal to 1, and so that is 1. But if I did it with my calculator, 16, math, probability, number 3, taken 0 at a time, I get the 1 also. All right? So now let's actually take a look at a few problems that involve possibly combinations. We'll see. It says an election ballot asks voters to select 4 city commissioners from a group of 8 candidates. In how many ways can this be done? Does the order matter? No. It's like the committee. Doesn't matter if you're first, second, third, fourth. So this is 8, combination of 8 taken 4 at a time. So it is 8, math. Number 3, we are taking these 8 4 at a time. There are 70 different slates of commissioners. All right, number 11. Of 13 possible books, you plan to take 5 with you on vacation. How many different collections of 5 books can you take? Now, you're not putting them on a shelf for display. You're just going to take 5. So order, once again, does not matter. So this is 13, the combination of 13 taken 5 at a time. 13, math, 3, taken 5 at a time, and that is 1,287 different groups of books. All right, number 12. You volunteer to help drive children at a charity event to the zoo, but you can only fit 7 of the 19 children present in your van. How many different groups of 7 children can you drive? It doesn't matter whether you're choosing them first or second or third, you just got to get 7. So order doesn't matter. So this is the combination of 19 taken 7 at a time. 19, math, number 3, 7, 19 taken 7 at a time. Well, there are 50,388 ways you could get your kiddos. Okay. Well, I think, no, this isn't our last one. We have, well, I seem to have lost number 14. I'll look at it. It says, to win at Lotto in one state, one must correctly select 7 numbers from a collection of 47 numbers, 1 through 47. The order in which the selection is made does not matter. Immediately that says it's a combination. How many different selections are possible? Okay, there, from 47, you're going to choose 7. Let's see how large this is. 47, math, probability number 3, and I'm only choosing 7 out of those 47, and I get 62,891,499. And I'm going to pause and see if I can figure out where my question 14 has gone. Okay, I'm just going to go ahead and discuss the 14th one. I really don't know what happened to the printed question, so I'll just talk about it. Number 14. It actually reads, in how many ways can a committee of 3 men and 4 women be formed from 12 men and 12 women? All right. In this one, we're going to find how many ways we could get our men and how many ways we could get our women. So we're going to have ways to choose men, and we're going to multiply that by the ways to choose women. That's actually the fundamental counting principle. So how many ways can we get men? Well, we've got 12 men, and we're going to take 3 of them. And order doesn't matter, so that's going to be 12, combination, taken 3 at a time. I'm using combination technique to simply find out how many ways there are to get 3 men chosen out of 12. But there are also some women to consider. I have to get 4 women out of 12 women. So I'm going to multiply that 12, taking 4 at a time. This is just like if I had 5 pair of pants and, well, it's not exactly like that, but when we used the fundamental counting theorem, we took the number of ways you could get the first one times the number of ways you could get the second one. All right, let's look at our calculator. And I have 12, math, combination of 12 taken 3 at a time, times 12, combination, taken 4 at a time. And I end up with 108,900. So let me put that back up there if you wanted to see it again. It was 12 taken 3 at a time times 12 taken, and it doesn't show, I'd have to, but there would be a 4. It didn't wrap around. That's what that little arrow means. Okay, so I'm putting a few things together to do this problem. Combinations just for the men, to count the different ways to get those. Combinations for those. Then the fundamental counting principle that tells me multiply this many ways times this one. In fact, I'm going to go all the way back and just show you the number of ways. If you can choose one item from a group of M and second from N, I know it's not 2 items, but it is telling me M times N. This one really says it. The number of ways in which a series of successive things can occur is found by multiplying the number of ways in which each can occur. So this is how many ways there were to get the men. This is how many ways there were to get the women. So I multiplied them, and they were both combinations. All right, let's do that lesson.